Hi everyone, and welcome to another episode of Global AI Notes. Today we're going to talk a little bit about GPT. Well, actually, we're going to look more into how some kind of models work. So stay tuned and learn more about how AI is working. And just as every week, we have a speaker from somewhere in the world. And today we invited Alan Smith. Hi, Alan.
Good morning, good afternoon, good evening from wherever you are. Hi.
Alan, from where are you?
I'm from the north of England, but I live in Stockholm in Sweden, which is a beautiful city, even though it's cold and snowy and icy at the moment.
Alan, could you please introduce yourself to the people who do not know you?
Yeah, my name is Alan Smith. I work for a company called Active Solution, and my primary focus for the past 2 years has been focusing on artificial intelligence and machine learning. It's been an interest of mine for about 5 years. I've previously worked a lot with Microsoft Azure, and we've really noticed ever since the GPT became popular about, 18 months ago, there's been a really big shift. So I've been working on quite a few projects involving GPT, quite a few involving vision as well. I've been working with Azure machine learning quite a lot, and then also fairly recently looking at working with numerical AI in Azure ML with the auto ML capabilities and model analysis. I also run a YouTube channel, which is at Cloudcast Alan Smith, and a lot of the demos I do quite a few training courses as well. So a lot of the demos I put up on the YouTube channel. I will be recording this as a demo, which will be a bit more polished. But as I was talking with Sammy before, I'm still working on the session. It's been quite a tough session to put together.
All right. Now today you're going to talk about the inside of GPT models, right?
Yeah, absolutely. Whenever I start to look at these algorithms, one thing that always interests me is, well, how does the algorithm actually work? How can an image model distinguish between a cat and a dog? And then when I saw the large language models, it just seemed like magic when you went on ChatGPT. And there's maths behind that magic. So what I'm going to do is hopefully explain a bit about how some of that maths works and what goes on inside the models. And you don't really need to know this to use the model, but understanding how the model works is going to help you to build better applications on top of these models. A bit like, if you're a racing driver, the more you understand about how an engine works, the better it helps you to drive.
Okay, great. Well, let me give you the platform. For the people who are listening live, please make use of the chat functionality on the platform that you're watching this on, and then we will ask the questions to Alan at the end of his presentation. So Alan, I'm going to add your screen to the stream, and with that, the platform is all yours.
Great. Thank you very much for that. I think I've covered all of this. Yeah, I didn't mention I also I'm an AI MVP. I've been in the MVP program about 19 years, starting off with BizTalk Server and running through Azure and ending up in AI. And I do quite a lot with conferences and speak at various conferences as well, and host the AI Burst conference. So before I start this session, I'd really like to thank the many YouTubers who've put together lots of great content that's helped me to understand this. I've spent hours watching different explanations of how these models work and how the maths works, and generally with machine learning, and these have been a great inspiration to this presentation. So a bit about GPT. If using GPT in many scenarios, I mean, mostly the most common scenario is you go into Copilot in Bing and you ask it a question. And what it does is you see it generating word by word or token by token, the actual responses coming out. And it's very good at being able to just take a simple question and generate a really good response on that question. This is mainly down to something called prompt engineering. I'm not going to talk too much about prompt engineering. That's really a completely separate session, and there's lots of guides on that coming out on YouTube and various other presentations if you do want to check that out. Another thing we can do is text generation. This is actually taken from an adapted scenario in a customer project. And this is when I was speaking at the Cloud Brew conference in Belgium, in Mechelen. Apparently, the Belgian, they get a lot of train strikes in Belgium, and that threatened to derail plans for the conference. So Gilles, Martin, and Chris were basically, trying to sort out getting all of the speakers to the events on time with all this chaos with the train strikes and so on. This is actually generated from this type of prompt, which is a few shot prompt where I'm giving a subject, a hero, a villain, and an objective. And it's generating one of these from these following examples, one of these inner world quotes that you get, as a trailers when you go to the actual cinema. So what it's doing is it's generating text similar to the example, but using my scenario of the Cloud Brew conference with the hero and the villain and the objective that they've got to do. We can also use it for fact validation. Again, this is from another adapted customer project where they wanted to validate text against internal policy documents. And what this is able to do is to detect that Stockholm is the capital and largest city of Sweden and not Finland. That was incorrect. And it was not founded in 2010 by Peter Ernholm. It was founded in 1252 by Bigger at Jarl. And being able to use it in different scenarios rather than just Q&A or chat with your data, and understanding those different scenarios is really good because these models are very powerful. They can do lots of stuff beside question and answering. Another thing is classification. In the olden days, which is in AI terms is about 2 years ago, if you wanted to do text classification, you would train a model to do text classification. Nowadays, you can use GPT, which is a pre-trained model. It will understand this text. I don't know what that means, but I think it's somebody tweeting something positive about the Tekorama conference. And it can actually give a sentiment analysis based on the actual text there. Another thing that's very popular is creating copilots. So if you ask GPT or the Copilot to give me a breakdown of the Nobel Prize winners per country in Europe, it's not very good at that because it's bringing all of the stuff from its model memory and going out and searching on the internet. However, if we have a database with the Nobel Prize winners in it, we could use ChatGPT or Bing Copilot, as it's called now, to generate a SQL query to be able to query that database and retrieve the information. So with copilots, we basically provide access for the GPT systems to access other systems. So it can run this query, it can write the query, it can execute the query, it can get the results. And from those results, it can then provide us with information. So for example, if it was querying your customer's sales database and you say, give me a summary of the sales in Sweden in February, it will be able to do that. It will be able to write that query and be able to give a text summarization of that. We do need to be careful here because if we ask it to improve the sales figures, we don't want it making update statements to the database and modifying data. So security and safety is always a high priority when we're working with these copilots. So processing text. If we ask how to make cheese, we've got this, thing which is a GPT model that's going to tell us how to make cheese. And the diagram of this was taken from the white paper, Attention is All You Need, which is really what kind of founded the development of lots of the large language models. So how do we get from this to this, going through this type of network? The main problem is that neural networks, they don't actually do text. You can't send text into a neural network. It does mathematical equations. So what we need to do is to be able to convert that text into numbers. And there's two stages in this process. The first stage is something called tokenization, where we're taking common sequences of characters found in text and converting them into integer values. So 3 things that are really important. The models, these GPT or large language models, they understand the statistic relationships between these tokens. You could argue that they don't actually understand text. They don't understand English or Belgian or Swedish. All they understand is the statistical relationships between these numeric tokens. So it's really just numbers that the models are processing. Second thing that's very important is that the GPT models, the only thing they will do is predict the next token in the sequence of tokens. So after text tokenization, it will basically say the next number in this sequence, kind of like those puzzles you do on like intelligence tests. You got like a few numbers, you know, what is the next two numbers in this sequence? That's what the models do. Third thing, this is really important, is that they are extremely good at doing this. They excel at producing the next token in a sequence of tokens. And because of that, and because of the way that we use these token predictions, we can actually get it to generate something that we can have a conversation with. So basically, this will look like this, separated in tokens. When we're working in English, most of the tokens are a single word prefixed by one space, or most of the tokens that are used here. You can see that GPT is split into two tokens there. And here we have the numerical values for these tokens. It's 45 tokens for that text. And the word "the," we can see it can be represented differently. Sometimes it's got a capital T and no space, in which case it's 464. Sometimes it's a capital T with a space before it, 363. It makes sense not to have space as a separate token, because that would use a lot of tokens, because if it's a word, the word usually has a space before that word. And you can see that we've got "the" with lowercase t is represented differently here. So it will understand the capitalization of words as well. If we do this in Swedish, then instead of being 45 tokens, it's going to be 83 tokens. And the tokenization language is really based on the most common sequences of characters that we get within languages. So in Swedish, you can see that bear is a language, bet is a language, and sorry, bear is a word, bet is a word, and ar is a word, r. And that's kind of why this barbetta is fragmented into three different tokens. If we go to Finnish, this is of the sort of common European and languages that use the same kind of alphanumeric characters. This is kind of the worst in terms of token consumption, and that comes out to 103 tokens there. You can see the words are highly fragmented here. Telugu, this was in the statistics as the most verbose in terms of token generation. So this is a Telugu, and for the same text talking about tokens, and this is what it looks like in tokens, and those are the integers, and it's 622 tokens. There's only 247 characters, but when you're working with kind of a non-alphanumeric characters, then Unicode sequences, it's more than one token to make up a particular character. So language is important. This is kind of a breakdown here of how efficient the tokenization is at generating the smaller amounts of tokens. You can see English is down here and Telugu is way over here. And you can probably spot, various languages along here, like Swedish. And as we go down, as we get into the less commonly used languages, we've got these languages down here. Telugu is a language, I think it's spoken in southern India. It's spoken over there. And this is showing the actual accuracy on I looked this up this morning. It's something like massive multi-language understanding, which is a test that we can do on the language models to determine the accuracy. And you can see that here with GPT-4, English is the highest accuracy, and as we go down, we kind of lose accuracy as we use different languages. So one thing that I've heard a lot over the past year is English is a new programming language. Especially when we're doing prompt engineering, we are basically telling our chatbot to behave in a certain way, to respond in a certain way, and to answer questions in a certain way, and maybe to a certain target audience. You could target it to, answer the question as if you were speaking to teenagers, or as if you're speaking to a 5-year-old or a physics professor, and it would phrase the actual output differently. So we've seen GPT models are most accurate within English. Billing is based on the number of tokens. So if you can minimize the number of tokens that you're sending to the models, things are going to be cheaper. Throughput is based on tokens per second, and models have a maximum number of input tokens. So using English is a way of providing an improvement in the performance, reducing the price, and also making the actual solutions more accurate. So it makes sense to use English. However, being an English speaker, I would argue that English is probably the worst language to use, because we have things like heteronyms. So if I looked up on Wikipedia what a heteronym is, and it's basically a homograph that is not a homophone. So basically what it is we get these various words where we've got wind and wind and tear and tear and dessert and desert and things like that. And this can confuse the language models because object and object are two different words. They're spelt the same, they're pronounced differently, but they will be the same token. So I would argue that English is maybe not the best choice for a model to understand a language, but it's the most commonly used language, so that's why it's the most prevalent. For example, I did ask in Telugu how to make cheese, and I got a very, very short response. Then the language model seemed to get a bit confused, and it generated an image of the frozen characters in an enchanted land, and it basically thought I requested that image there. Hopefully in the future, we will see better language support for these less common languages. You can train your own model based on your own language. So GPT-3 is based on Swedish, Norwegian, Danish, Icelandic, and English, and some programming code. And you can download that model, and you can work with that model if you want to. And you can also train models based on your own languages. However, people I've spoke to who've used the Swedish model, they've found that using GPT-4 provides better accuracy than training your own model on a specific language. Because here we see GPT-3, 70%, and most of these languages, GPT-4 is better at Punjabi than it is than GPT-3 is English. So it makes sense to use a multi-language model. So a bit about the tokenization. There is a website that can do this for us, and is this language tokenizer. So if you want to know how many tokens you're working with, you can see the number of tokens there. You can see the number of characters there, and you can see the token ID. So that can help you to understand how many tokens are being generated. Also, if I iterate through the tokens, if I just start this without debugging, this is actually the GPT-2 model, which isn't that great in terms of performance, but we can download the source code and we can step through the source code, which is what I'm going to do in this session. So these are the tokens that GPT-2 is using. We can see the first 256 is just basically the ASCII character set. Then we get into various words, and the most common words tend to be lower down in the token. So we've got like not, and then we've got these kind of parts of words here from the various tokens there. So these are basically used to make up the actual language. However, if you've worked with neural networks, they don't really do integers. They deal with floating point values. So what we've got to do is a process called vectorization. So if we take the word cheese, there is a vector table in the language models that will have the actual token vectorization for that particular token. Now, I've written word vectorization. That's normally what we talk about, but it's really token vectorization in the GPT-2 models. And I think there's 768 floating point values. That is kind of this numeric representation of the word cheese, and this is what the GPT models will be processing and doing all of the maths with to predict the next token. Now, this is high dimensional. We can't really understand 768 dimensions. We're good at understanding 3 dimensions. So if you've worked with any kind of graphic development in using computers, you know that colors can be represented using the red, green, and blue values. So if we convert that to floating point values, this is the actual vector for Azure. And we can project all of these colors into a 3D space, and you can see that similar colors are grouped together. And the idea with word tokenization is that similar words can be grouped together. So the earliest research on this was something called word2vec, which is a way of being able to vectorize words. And in theory, they say that you can do maths with words. So they say king minus man plus woman is equal to queen, and Paris minus France plus Poland is equal to Warsaw. Because we're looking at the capital city. If we take Paris, we take away France and add Poland, it should be Warsaw. I've tried, but I couldn't get this maths to work with those particular sums. But this is kind of a lot of the theory that they talk about. The vectorization allows the models to do maths with these actual vector arrays of the tokens. Embeddings Projector is a really cool site for kind of visualizing how word2vec works. So this is 10,000 words. I'll just turn it to the dark theme. And if I change this or search for February and just look at the closest 11 matches to February, you can see that we've got the various months appearing here. And what I can do is we can basically work with nearest neighbors. And what this will do is basically group the words that have similar meaning and similar sentiment together. And once it does that, we should see these months that are highlighted move together into the same amount in 3D space. So what we're doing here is we're taking in word2vec, they've got 200 parameters in the actual tokens, and we should be able to see if I can just select February again. We can see that what this is doing is it's figuring out that these are basically fairly common words that have a lot in common. So you can see that March and April and July are kind of grouped together in the same space. And that vectorization is used to allow the models to kind of understand the relationships that these tokens have with each other. So that's on projector.tensorflow.org if you want to play around with that. We can also use vectors in vector databases. So a lot of work that's taking place now with large language models and searches is taking text and embedding the text or vectorizing the text into a vector database and finding the nearest neighbors and finding text with similar sentiment. The Azure AI search that was formerly known as Azure Cognitive Search, that has vector capabilities within it. And it means we can also do cool things like taking an image, vectorizing the image and then searching for similar images. And the way that Spotify uses this is they want to find similar songs. So you can take a song, you can vectorize the song, and you can find songs that sound like this particular song. I've played around with this bit using Spotify Annoy, which stands for Approximate Nearest Neighbors. Oh yeah. So when I was generating the nearest neighbors in the projector website, this is the same thing that we can do with songs, with images, with text, and with anything really that we can actually vectorize. So sequence prediction, what we're looking at doing is predicting the next item in a sequence of tokens. These can be variable length, so we can have short sequences if we put in a long question or we're sending lots of data into the prompt. These can be very long sequences. And all the model is going to do is to predict the next item in that. We have all kinds of challenges like long-term dependencies. So the cat sat on the floor. It had just been cleaned. So what had just been cleaned? Was it the floor or was it the cat? And we can understand that because it had been cleaned, it should relate to the floor. And if the cat sat on the floor, it had just been fed, then it would relate to the cat. So we kind of have all of these dependencies. If we get more complex input, like the boy stood on the burning deck poem, it mentions the boy in the first verse. And in this verse here, it's saying upon his brow he felt their breath. Well, his is referring to the boy. And there's a lot of long-term dependencies running through that particular piece of text. Order is important. The film was not bad. In fact, it was very good versus the film was not good. In fact, it was very bad. We've swapped the position of two words and given it a completely different, the opposite sentiment there. Order is important as well. So all the model is going to do is it's going to predict the probability of the next token. The cat sat on there, and we've got various probabilities here. And what it's really doing is just taking these numbers and predicting that 4314 is going to be the most probable token to follow that sequence there. The king of rock and roll is Elvis, and then we've got Prez being the next probable token here with 64.98%. Cost here, so it could be Elvis Costello at 2.76%. So looking at sequence prediction, what I'm going to do is to use the GPT-2 model to do the next token prediction. I think it's actually this GPT fundamentals demo that I need to set as the startup file. And I'll just do a Control F5 on that. Sorry, Control F5. And what this is going to do is just going to show us for some sequences of text the next probable token. So we can see we've got the cat sat on there. And here we've got Stockholm is the capital of. We've got Sweden here at 42.23%. However, Norway is coming in at 7.13 and Denmark at 4.21. So I'll talk about temperature later on. Using the temperature is a way of making sure that you select more probable tokens and you don't select random tokens. If you imagine that this is one of those, wheels at the fairground that they spin, and there's a 42% chance of it landing on Sweden and only a 4.21% chance landing on Denmark, but it could land on Denmark. So using temperature, as we'll see later on, is a way of controlling the output to make the output more predictable and use the more probable tokens there. It also understands code. If you've ever asked GPT to write code, it understands that using system dot, we've got various things, .out, .windows, .thread, runtime, and these are all things that you can have after system dot. And then if you're a Python programmer, import numpy as. Pretty much everybody uses NP when they import numpy, and it's giving us that prediction there of a high prediction there. And then we've got the king of rock and roll is Elvis. We've seen that one. However, if we say the king of rock and roll is Elvis Pres, then Lee, without a space, is 99.76% the next token. Same thing if it's going to be Elvis Costello. If I say cost, then LO is coming out as the next token there. And then if you look at favorite animals, you can see that this is something where somebody's favorite animal is very subjective. We can see that there's a much more of a spread of probabilities there with that one. Okay, back to the slides. So there's a bit of an evolution in getting to the transformer models that we're working with now. So we went through recurrent neural networks, long short-term memories, and eventually ended up with transformers. I'll run quickly through these. The recurrent neural network has a hidden state. So as we're doing a sequence prediction, the hidden state is passed to the next iteration, and we feed in the tokens one by one. One of the problems of this model is that by the time we get down here, because the hidden state has passed through all of these different iterations of the network, very often information and context can get lost. So LTSMs was a way of treating this hidden state as short-term memory and then adding on long-term memory so it can remember more about what was earlier on in the sequence. And these were very well used until the transformer architecture came along, which is this thing here. So we'll look at a bit about how this works. As I mentioned, this is from the Attention is All You Need white paper. So first thing we want to do is to forget about the output embedding. The white paper was written about language translators, and we're not using it for translation, we're using it for token prediction. So we don't send in output embedding for the target language, we're just focused on the input embedding. So we'll look at how this actually works in the model. We first do the tokenization. So the cat sat on there is going to be tokenized. We then do the token embedding. And as I mentioned, once we've got the token IDs, there is an embeddings table for these tokens within the network itself that has these 768 floating point values. And we just do a lookup based on this ID, picking the particular ID from the embeddings table. And that gives us our embedding vectors for these 5 tokens, which is going to be 5 because we've got 5 tokens, and 768 because that's how many floating point numbers that we're using. So that gives us our embedding vectors. The next thing we need is the positional vectors. And these are fixed. So we've got position 0, 1, 2, 3, 4, and 5, having various sequences of numbers. And these are always the same. And they're calculated from like sines and cosines and various mathematical formula to give each token a unique position within that sequence, because position is important, as we saw earlier. So we then add those two together, and that gives us our encoder input vectors. So if I switch back to the code and I go back to next token prediction, I'm going to set this as the startup file, and I'm going to run this in the debugger. And what I'm going to enter, if I just press enter, it will say the cat sat on there. It's going to take a couple of seconds to load the model. And we should go into debugging. If I can find where we are, I'll probably need to... Oh, that's the immediate window. Yeah, let's move that down and see where we've hit. We should have hit a breakpoint. Yeah, so here we are. If I go into the watch, you can see that we're in the GPT-2 model. here, and we've basically been passed in the actual inputs. If I press F5 again, okay, I'll just check my breakpoints. Yeah, I seem to have skipped a breakpoint here, so let's go into the call stack and see if I can find where I should have been. I'll just try that again, actually, and start that. And what I was looking for is the actual calculation that is going to figure out the actual embedding vectors. I hope I haven't removed that breakpoint, because it should have been hitting that. Yeah, I think I removed that breakpoint. It was on the one that was actually looking at the figuring out the actual hidden. Oh, here it is actually. Yeah, we've hit it. So what we're going to do here is we've got our inputs. If you look at the input IDs, you can see these are the tokens for the cat sat on there. And what we're going to do is to get the input embeddings, and this is in an actual embeddings table, which is this thing here. If I do an F12 on that, it's not going to take me to the definition, but what this is just going to do is to do the embeddings. So if I step over that line of code, we've now got the input embeddings, which is basically a lot of floating point values. And you can see the size of that is 1, because there's kind of one batch, one sentence for processing. There's 5 tokens, and there's 768 values there. We then get our position embeddings. So this is coming from the positioning tokens. And this is, again, another tensor with the same dimensions, 1 by 5 by 768. And then we're doing hidden states is equal to input embeddings plus position embeds. And that's going to calculate the actual hidden states, which is the encoder input values. So the next thing we're going to do, this is when the maths gets a bit more tricky, is look at the multi-head attention. Now, there's many different layers, and there's 12 heads in this, but this is basically the attention formula. That's a key of how these language models work. So don't be daunted by the maths. It is quite complex, but the basis behind this is we're using a query, we're using a key, and we're using a value. And we're using that to be able to calculate the attention, which is going to give us information about our input that can then be used by the model to predict the next output. So the encoder input values, that's the 1 by 5 by 768, that runs through a convolutional layer. And that is going to generate a 1 by 5 by 2304. 2304 is 3 times 768. And this is going to generate the relevant information that the attention mechanism needs. And this is then going to be split into 3 different arrays, which is the key, the query, and the value. So if we drop back into the code, I think if I do F5, we're doing that operation there. We're taking in the hidden states, which was the encoder input values, and we're running them through this attention layer, which is a 1D convolutional layer. We're then splitting them, and that's giving us our query, our key, and our value. So if I step over that line of code, then we'll actually calculate that query, the key, and the value. Now, because there's 12 heads in this particular model, if we drop back a couple of slides, we saw that this is a multi-head attention. It's actually using 12 attention heads. So what we do then is in split heads, we basically get for the query, the key, and the value, this 1 by 12 by 5 by 64. There's one batch, there's 12 heads, there's 5 tokens, and because we've split 768 and divided it by the 12 heads, we've got 64 floating point values in there. Then we actually do the maths, which is this sum here. And I think we can see the code for that if I just drop back to Visual Studio. We're doing this torch.mathmul, which is a multiplication by the key and the value, and that's giving us the attention weights. And then we divide it by the square root. That's going to give us the actual output of that formula. So if I step through this, we're actually calculating the attention weights. You can see we've got this 1 by 12 by 5 by 5. And that's going to happen lots of times. because we've got these 12 different heads. And as I'm running through this, you can see it's going through all of the various layers there. So what I can do is I can just disable these breakpoints that we are hitting. So if I disable that one, and disable that one there, eventually we'll get to the actual output. So I'll drop back to the slides, and we've been through that stuff there. Basically, the query is going to be the current token that the model is focusing on. The key is going to be a token from the input sequence that the model is comparing to the query, and the value is information relating to that relationship. So what it's really doing is it's building up a matrix of floating point numbers that describe how each word is relevant to each other word within the sentence. So if it was the cat sat on the mat, it had just been cleaned, then there would be a reference between it and mat. You basically have all of those kind of word associations. And that's kind of what's used to generate the attention formula. So this is numeric information about the meaning, the position, and the relationship to other words within those sequences. I've only got 5 here, and the maths is already kind of really confusing me. Imagine what this is like when you've got thousands and thousands of tokens. There's lots of maths going on inside these complex models. So to try and explain that, all of this vector maths is really just doing transformations. So we've got all of these tokens from these kind of 2 sentences, like it and cat and fed and floor and cleaned. If we just take the first sentence, then there is more connection between it and floor and it and cleaned. And because of that, what it's able to do is it's able to move the word it in the vector space to be closer to floor and cleaned, because it has more of a connection with those words there. Remember, in the embeddings projector, when words that are related to each other will be kind of moved towards each other in that multi-dimensional space. So all it's really doing is predicting the next item in the token, the next token. We then add that onto the sequence, and then we get the next token, which is comma. We add that on, and the next token is and we add that on there. So let's look at how that works if we just use the model to predict the next token. So I think I had that one next token prediction set as a startup project. I'm going to do a Control F5 and run this without the debugger, so we don't hit all those breakpoints. So the cat sat on there, and I choose the next word. The cat sat on the floor, and the cat was still asleep. And all I'm doing is I'm just pressing enter, which is choosing the next token in that sequence. And as you can see, this isn't too great. It's just got stuck in a loop saying, I'm sorry, I'm sorry. So if we want some variation in the text, then we kind of have to not choose the next probable token, but just choose other tokens as well. So I could choose 8 for very, and then 6 for grateful, and then see what it's going to do now. I'm sorry. And then we can have said Harry. That's going to be 2. Potter. Okay, that's going to be 2 again. And as you can see, by varying those tokens, it is able to actually generate sentences by not choosing the most probable token there. So drop back to the slides, and sorry, there's that one here. One of the ways that we can vary this is with the temperature. So depending on the model, in GPT-2, it's between 0 and 2. In others, it's usually between 0 and 1. And that is basically going to govern how probable the next token is. So if we set it to 0, it's going to generate the same result every time. So if we want to do something where we want that to happen, like text classification or querying a SQL database, we can use that. For other solutions, we may want to choose this as 0.5 or 0.7 to 0.9 for if you wanted it to be more creative with stuff. So looking at how token works, what it's doing is it's taking the scores and it's dividing them by the temperature, and we'll see how that works when I run in and just quickly debug the model. And then we're performing a softmax operation on this. I'll explain how this works in the form of a demo. It's quite a complex formula, but really the softmax function is converting this kind of vector of floating point numbers into a percentage probability distribution, which is what we see when we look at the token probabilities for the model. If you've worked with neural networks, then you've probably used softmax a lot for doing predictions. It's usually the last activation function that we're using in neural networks. So you will have played around with that if you've used PyTorch or TensorFlow to build and train your own models. Okay, so looking at how temperature affects things. If I go into, I think this is the first one I want to run this temperature theory. So if I set this as the startup file and just hit Control F5, what this is going to do is it's going to run the prediction 5 times with a temperature of 0.0. And you can see here, my favorite animal is a dog. It's a very good dog. It's a very good dog. It's a very good dog. That's not too good. However, if we start to go for a temperature of 0.1, you can see that we are starting to get some variation in those. However, it's always dogs that is the most probable one here. Then with the temperature 0.2, we've actually got a couple of pandas coming in here. And as we increase the temperature, we're going to be getting more variation in the actual text, and it will get more creative. So as you can see as we go through these, I've been delivering this presentation in front of live audiences, and sometimes the audience just falls about laughing, and I haven't got time to read through what it's come out with. It can sometimes come out with some unpredictable stuff as we do start to use the higher temperatures there. So looking at how temperature theory works, I'm going to set this one as the startup project, if I can do that. Okay. Yeah, set a startup file. I'll just do a Control F5 on this. And what this is going to do is it's going to take my favorite animal is there, and it's going to show us the actual probability distribution. And you can see here that there's a very small chance of dog being the next one, because it's something that can be many different answers of. However, if we start to reduce the temperature, if I go with a temperature of 0.9, you can see that the percentage that dog is going to be chosen, and also these other ones, is actually increasing. So this is now on 3.49%, and here it's now on 5.21%. And as we go down the temperatures, you can see that the probability of dog being the next chosen one is increasing all of the time. So that's on 0.4, and then if you go to 0.3, it's almost 50%. 0.2, that prediction comes out as 76%, and then 0.1, 97%. And if we're using a temperature of 0, it's pretty much 100% that it is going to be that particular token that is chosen, which is why in GPT-2 it was very predictable with its outputs when I was using a temperature of 0. There's a few other parameters we can use as well. As well as temperature, we can use top P. Now, the recommendation is we should either use temperature or we should use a top P. And what top P says, if I select a top P of 0.2, it will choose the first 20% of probability, the actual tokens from that. If I select 0.45, it selects from the first 45, and there we've got the top P on 0.75. It's going to select a lot more stuff. So it's two different ways that you can control the predictability of those outputs. Other parameters we can use, like how many check completions it's going to generate for each message. We can have various stop sequences. We can specify a maximum number of tokens to generate. And then we've got presence penalty and frequency penalty, which will prevent repetition from coming in those various models as well. We can also bias various items from appearing within the actual completion there. So I'd mentioned a bit about softmax. So in this one, what I was doing was I'm getting the actual predictions out. I'll just finish off with showing how this works by debugging this. So what I'm getting out from the actual models, if I just drop a breakpoint there and run this with the debugger, we should hit this breakpoint, which is going to get us the next token logit, which is going to be the floating point numbers that kind of represent the word probabilities. Now, if I go into the watch window, into the immediate window, and we just drop in next token logits. Oh yeah, sorry, I've just got to actually get that output. So if I do F10, we see that we get this big array of floating point numbers, and these are not between 0 and 1. We've got like -80, -83. So what we're going to do is we're going to take these actual values and we're going to divide them by the temperature. Now, if the temperature is 1.0, we're just dividing them by 1. And that means that they'll just have their original values, and that's going to make these things fairly unpredictable there. So if I F5 on that, that was giving us these predictions here. However, as temperature increases, if I do F5 and F5 again, and F5 again, that means that the temperature is now 0.6. And this means that if we divide by 0.6, we're kind of increasing the values. And then when we're actually using the softmax formula, that's kind of changing the probability distribution and favoring the more probable tokens. So it's a really simple bit of math just to divide by the temperature, but combined with the softmax formula, that really works well in giving out the actual predictions for those language models. As well as using those, we also use something called a beam search, and this is used internally within the models. And what this is doing is, instead of just choosing particular tokens, what it will do is look at various combinations of tokens. So the cat sat on the floor, comma, and the, or and comma his head. And what it will look at is various groups of tokens. So it can actually say, well, instead of just saying floor, let's look at a few different possibilities and see which kind of combinations of tokens are going to be give the most predictable output there. I've not really explored too much on how beam searches work, but it's something that you can configure when you're working with a GPT-2. Just to show, finally, my final demo. I know I'm taking a bit more time than was expected. Just to show how things have evolved, I built this, which I'll set as a startup file, which is called ChatGPT-2. So what I'm doing is just building a simple chatbot, but instead of based on GPT-4, it's based on GPT-2. So I can say, what is the capital of Sweden? And it says the capital of Sweden is Stockholm. That's cool. Is it nice there? Yes, it is nice. Are there animals there? No, there are no animals in Stockholm. Are there lions? No, no lions. But there must be cats. No, no cats. Why are there no cats? There are no cats. So yeah, I remember when my kids were about 4 or 5 years old, you used to have these kind of conversations with kids that went something like this. This kind of shows from GPT 2 to 3 to 3.5 to 4, just the incredible pace of evolution that we've got in these language models. This can just about answer questions, though it's not very good at it. But you look at what these new current language models are able to create now. It is pretty incredible. Okay, so that's all I was going to run through. I will, at some point in time, record this and put this out on my YouTube channel. And so if you do want to run through it again and kind of see a more polished one where I don't make small mistakes in the demos, then feel free to do that. But thanks for listening. Just wondering if you've got any questions that you would like me to go through.
Okay, what a serious in-depth session was that. It was quite interesting to learn more how these LLM models actually work. I also learned quite a lot. I had some basic knowledge, but this opened my eyes. And it also helps you understand why this kind of models, well, why you can't just run them easily on your computer, that you need some serious compute with all this
Yeah.
calculation.
Yeah, I mean, you can just about train a GPT-2 model in your own machine, but you need a pretty hefty GPU for it. I've got like an RTX 3090, and I think it took about 5 hours to train a basic model on like song lyric prediction, so it could just about generate lyrics for songs. But you really do need a cloud and a supercomputer to work with these these really big models that Microsoft and OpenAI are working on.
Yeah. Well, Alan, we don't have any particular questions that came from the public. I think you explained everything also quite clear. It was very nicely done. Thank you for that. We thank you for your efforts you did in creating this presentation. Looking forward to learn more about other presentations that you've done, or to see you at events all over, anywhere you're. Any plans for speaking anywhere at the moment?
Yeah, I'm speaking at the MVP Summit in a few weeks, and then I think Tekorama, Belgium. I'm going to be delivering this session at Tekorama, Belgium, and then also GoTo in Amsterdam. I'm actually doing a session on GPT-4 playing StarCraft, which is something I've been YouTubing about at the moment, which is interesting to see how we can use a language model in a strategic decision process and actually connect it up so it will actually do stuff with the output of the model. And I'm using the output of what's coming out of GPT-4 to actually run a StarCraft bot and decide on how it's going to play StarCraft. And it's doing a pretty good job of it, which surprised me.
Okay, cool. Well, if you have not seen Alan's YouTube channel, maybe Alan, you can repeat what's the link or the channel name?
Yeah, I had it. So it's Cloudcast Alan Smith. So yeah, I dropped it up there. There's a link there.
Let me put it back on the screen.
I don't know if we could put it in the notes as well. If
you put it on the private chat, I can put it in a banner.
Yeah, I'll do that. Yeah.
We'll put it in one of the chat messages that can be seen. Cool, great. Thank you very much, Alan. For everyone who's still listening, have a great day, and we're looking forward to see you next week again. Bye-bye.
Great.